All right, we will go ahead and get started. Again, thanks for joining us for this edition of the Pigment 101 webinar. We're happy to have you. And we will go ahead and get started. As usual, I am recording this session, and all of those in attendance will be able to get the link for the recording as well as the PDF of the presentation. And if you have any questions along the way, feel free to put them in the chat box, and I will address them at the end of the presentation. And from there, we will take it as well. So we'll go ahead and get started. And so today we are going to revisit a subject I did several years ago, which is the DPP chemistry in there. So they play a very good role in there, so that um, that they provide that in there. So we'll go ahead and get started. Anyway, so the DPP chemistry is part of the polycyclic group of organic pigments. They are part of the high performance uh, uh, grouping of pigments. And so they play a very important role in the world of organic pigments. So, we've reviewed this in the past before. The high performance play a role. They are going to give you your formulation that very high light fastness and weather fastness, heat resistance on the high side, good resistance to solvents and chemicals in there. So there's a lot of value in the performance of these types of pigments, as well as the coloristic attributes for them as well. So red pigments, this is where the DPP type chemistries shine. It's one of those colors that does naturally draw everybody's attention to it, thus the stop sign and the red Ferrari there. Um, they are brought into this world to fill a void that the classical pigments have, which is really the chroma, but also the technical properties. So the family of DPP pigments, both on the red side and the orange side, they're going to bring superior chroma, as well as those high performance properties that might be needed for your application. A little bit of a historical timeline. I thought this was very interesting, so I wanted to share this with you as well. This just gives a feel for how how different classes of pigments came to be. So if you recall, pigments naturally were natural colorants from the get-go, drawing from either the minerals in the earth or plants and the like, to be able to provide the color. Unfortunately, those things are not as durable, light fast, and easily available. So lo and behold, the scientists of the world have started to create the synthetic pigments and be able to. So the monoazos were the first major synthetic organic pigments introduced in there. So pigment yellow 1, thus the name, was the very first synthesized pigment to be introduced into the marketplace. Diazos followed that. Phthalocyanades came after that. Quinacridone started the first high performance, truly high performance types of pigments when they were introduced in the 1950s, early 60s. The isodolanone were also high performance in there, but to the yellow and the orange side of color space. Then the benzimidazolones came along, and they were really brought online to be a little bit still high performance, but to take that monoazo that azo chemistry to the next level, to get the coloristics and some of the value from the azo chemistries, but to get the high performance properties, thus the birth of the benzimidazolone type chemistries. Following that is the DPP chemistry, which we'll talk about today, as well as the parallenes in there. So this gives you a little flavor of how these types of chemistries came to light in the industry. If you also think about them from a generational perspective, so first generations were the classical pigments, the monoazo, diazo, phthalocyanines, and the like. So the second generation would be the high performance one, or the first generation of high performance were the quinacridones and the isonolones and benzimidazolones. The premium high performance or third generation then would be the DPP and parallene type chemistries. This is a very interesting way to look at it, because obviously if people did not have a open need for something, it would not be invented. So I like this slide because people are asking questions. So in the 1990s came the question, can we make bright synthetic colors? Thus the thus the azos came on board. And then in the 1930s, can they be stronger and more economical? 1950s, can they survive outdoors? The 1970s, can they withstand engineering plastics and automotive coatings? Very robust types of application areas. And then onwards from the 1980s, can they deliver both exceptional chroma and exceptional durability? So the progression does show how the demands of industries um, uh, necessitate these inventions and chemistry developments to be able to match what the industries demand. So from a color paste perspective, so in the red space, I've highlighted it here in these white circles, the DPP chemistries and where they sit in color space. So the pigment red 264 is going to be your more blue in color. The more neutral would be the pigment red 254. And then to the yellow side is the red 255 and red 272. And from a Sudarshan perspective, portfolio perspective, the bold circled ones are the color indexes that are in our portfolio. And on the orange perspective, there are two. The orange 73 is to the redder side, while the orange 71 is to the very yellow side. Oops. So a little bit more about them. So a little, some history we've already covered in the previous slides. Just a little bit about where they fit in. So 254, the easiest way to think of red 254 is think of Ferrari red or Coke red. That's a good way to visualize where that color space is fit. And then if you take that to the bluer side, that's where the pigment red 264 will fill that space. 264 is a very good one, especially on the automotive side, because it's very transparent. So it's a great match to pair with effect pigments to allow for that maximum visual effect from those effect pigments. All right, from a chemistry perspective, so they all share the same background, backbone, I should say, in there. And depending on what that aromatic is associated, that's attached onto that to that backbone structure, will dictate the color index, which then results in the color shade of that particular DPP chemistry. So if you start at the top, that aromatic unit with the chlorine on it is the red 254 that gives that um, medium mid-shade red color perspective. Then you can see how the 255 and 264 and the red 272 are created, and the aromatic units that are attached in those two locations off of the backbone to be able to get that. And then on the orange side, same idea here, same two locations on the backbone, and the aromatic units that are used for that to be able to create those color indexes and those shades. Now, a little bit more details with respect to each one of these. The Pigment Red 254 is what I call a workhorse DPP chemistry, because it is something that is widely used in multiple application areas. It's got a lot of very good properties that bring value to that particular formulation. So it comes with it, obviously, all of the various technical properties that go along with high performance pigments. One thing to keep in mind as you're using this chemistry pigment is that it's going to be TiO2 sensitive with respect to weather fastness in there. So one way to kind of formulate around that, if you need to be in that more pastel shade area, is to get there a different way, perhaps using for a yellow 53 CICP to get that lightness, that opacity part of it, along with the red 254 to gain that durability, exterior weather fastness that might be required for that one. In other areas, especially on the water-based coating side, this type of chemistry can be sensitive to flocculation. So it's important to make sure that the proper dispersant and additives are chosen for that particular formulation, to be able to keep that one in suspension, in dispersion stability perspective. What can Red 254 do for you? As I mentioned earlier, it's a more of a neutral shade red, so it allows you to shift the color that you're looking for, either to the red side or excuse me, either to the blue side or to the yellow side, using other high performance pigments to get to the shading space that you're looking for. For example, shading with a isoindolino, a pigment yellow 110 is a great example, shifting a red 254 more yellow in there. Still have that same high performance technical properties, but you get to that space that you're looking for. Likewise, to the blue side, you can always use red 264, staying in the same chemistry family, or even with a CPC blue is a good way to get there as well. On the mass tone area, does have very good weather fastness in that area, and it's it's fast with respect to bleeding in terms of plastics as well. So all in all, a very useful tool in your colorant toolbox. From a Sudarshan perspective, as I mentioned, it's part of our portfolio in various powders forms. We have a number of brands that are active in all types of application areas, as well as a number of dispersions that are available as well, utilizing the Pigment Red 254 pigment. Shifting to the next one in the list is the Pigment Red 255. This is much more yellow in shade versus the Pigment Red 254. And really, the numbering system doesn't have any relation to the color shade in here. It's just the number that was assigned to it when it was developed in here. So, like other DPPs, it's always going to have that a good outdoor durability, and it does because it's very much on the opaque side, provide that excellent hiding power. This is not a color index that's in our portfolio, but it's always good to know about it to be able to potentially utilize it. Pigment Red 264. As I mentioned, this is to the blue side. It is certainly available. It's most likely in the transparent versions, although there are opaque ones or more opaque versions as well. But primarily, it's the transparent grades that are the most important grades for different application areas. As I mentioned, these are great when used in conjunctions with effect pigments because they are very transparent. They're going to allow that deep DOI, depthness of shade with respect to the effect pigments in there. So you get a lot of value and utilization of your effect pigments when used in combination with the Red 264. It, like other high performance pigments, selection of the dispersant is always important, especially in these high performance areas, for a number of reasons. As you want to be able to get the most value out of that pigment in there. So increasing the strength is always a key in this area, and the selection of the dispersant can also make that happen. What can Red 264 do for you? It definitely brings those high performance technical properties to your formulation. This chemistry is not impacted by the TiO2 photodegradation, so it's excellent with respect to all shades of color with respect to the weatherability. We have a couple of options in this chemistry available in the powder form in here. So these are these are key products, especially on the automotive side, and also from a coatings perspective, but also in the plastics area in the automotive side. These do tend to show up a lot for these properties. Moving on is the Pigment Red 272. This is one of the ones that is is also to the bluer side, especially when in combination with TiO2. It has very good chroma. It's a little bit to the yellow side, although not as yellow as the Pigment Red 255. Very good for hiding, and obviously does carry with it the same high performance properties that come along with the DPP chemistry. Moving to the orange shade is the Pigment Orange 71. This is can be a very good product for a lot of areas. It's a more transparent type of pigment in there with of course the excellent heat stability and migration fastness part of it. And then Orange 73, this is a more medium shade orange pigment, tends to be more to the opaque side in terms of opacity, similar in opacity to the Red 254, for example, in here. We have this in the dispersion form within Sudarshan product portfolio. So synthesis is always key when it comes to organic pigments, and this is not something that is new to you all there, and as well as finishing to be able to get that end product in here. So the DPP chemistry is probably one of the more complex when it comes to synthesis steps in here, and some key ones are key in terms of getting to where you want it to be, where you want that end product to be. So a little bit of a brief process steps in here. Two very key synthesis steps with respect to this chemistry. As I mentioned, it's very complex in the synthesis. Typically, you only see one step in these reactions, but this one does have two. But from a product perspective, the two main areas that are of great importance in creating each individual product and grade is how we handle the quenching process, which that stops the actual crystal growth itself, as well as the what we call the pigmentation step that creates that final product in there. So those are the two key steps within the process. And just to give you a feel for that one, so you get a better feel for the two synthesis steps that are in there and what they do. As I mentioned, the two key steps for quenching. The quenching then basically establishes that crude that you've created during the synthesis process. This sets up the product itself for the particle size and the opacity that you're looking for in this particular step. And then once that's created, that the crystals are then grown and other surface treatments are used as needed for that particular product and grade. And that is all going to dictate the shade and opacity that the end product will take on based on the conditions used in that particular step. And then, like other pigments, the filtration and surface treatment is done to create the dispersibility and further the opacity or transparency, depending on which direction you're going. And then, of course, they have to be dried and pulverized to get to that final product as well. So I thought it'd be very interesting to offer you some comparisons of the DPP chemistries in the red space to other red pigments, because there's a variety of pigments to choose from in the red space, as my earlier chart showed. So I thought it would be interesting just to have some comparisons, both with other high performance pigments as well as some more traditional pigments as well. Taking a look at what each brings to the party, what limitations might be there in there, because ultimately it's when do you choose a DPP over other red pigments in there. It's good to understand where it excels, or where another chemistry might be a better choice for your application and formulation. So, as you well know, there's no single red pigment that's ideal for every application in here. So as you're selecting pigments, you're going to have your list of attributes that you're looking for. And each application will have its own attribute list to be able to get to that end point in here. So these are just a few things that are done when choosing a red pigment for your application. Um, I we do know that the DPP pigments occupy that premium end. It may be overkill for your formulation, but it may be a requirement for all of your attributes that you're trying to achieve. So versus quinacridins. So from a color perspective, DPP, think of the Ferrari red. With quinacanones, think of deep ruby or red wine in terms of a color perspective. So they are going to have different color shades in there. Their properties are very similar. They're both high performance pigments in there, where the quinacanones might be greater from a heat stability perspective. So maybe on the plastic sides, that there might be some attractiveness with that as well. But in all other properties, they're both in that high performance category with respects to the technical properties. They just occupy different color spaces. So that brings us to when to choose a DPP space when you're looking for that more bright red or an orange red. A lot of times these show up more in automotive type areas and high performance plastics as well. When quinacridone tend to be one where you're looking for the more bluer shade of red, or those violet reds, magentas, that's kind of things. But from a application perspective, they both fit the same application areas between the two. It just really is that color space that you're trying to achieve. Naphthol reds. So naphthol, I classify naphthol reds as that intermediate between classical pigments and the high performance pigments. They have characteristics of both in here. So from a color perspective, they both offer bright reds. So consider Pigment Red 254, Pigment Red 170. Both fill this very similar color spaces. They just offer different technical properties to your formulation. And that's really where they are different when you compare one chemistry versus another. It really does come down to that the property differences between the two. So this chart certainly gives you a very nice flavor of those differences in there. So again, it's really choosing and matching your application needs and color space. So, they have similar applications, but also different ones in there. So we tend to see the naphthol reds more on the decorative or printing side, indoor plastics in there because they just don't have as good of durability as the high performance areas. Where the DPP chemistries, we start to see them in more rugged and demanding applications like automotive and plastics, powder coatings, those kinds of things, to be able to take advantage of those technical properties. So it really is what your application and formulation demands. If you need those longer warranties and outdoor durability, then the high performance type pigment is where you need to be to get those. Benzimidazolones, this is not usually a comparison that one would consider because primarily benzimidazolones fill that orange to yellow space where the DPP chemistries fill the bright red to the deeper scarlet red. But they do intersect in that orange space with, for example, the orange 71, the orange 73 crosses over with orange 64, for example. So there is some overlap in terms of a color space between these two in there. And then similarly, they do have very good properties as well in there. So it's just some other options to consider in there because benzimidazolones because they are high performance azo pigments, they sometimes can get overlooked as well. So again, it goes back to that color space that you're looking for. the benzodiazepine's occupy that yellow to orange shade space, whereas the DPP chemistries do occupy the orange space, but then towards the red space as well. Pyrrolines, both are what I would consider the premium high performance color space. And really, again, it comes back to a color space difference between the two. The DPPs tend to be the brighter, um, cleaner, or more oranger shade reds, versus the Pyrrolines tend to be the dark reds, the maroons, or deep violets, those types of color spaces in there. But from that perspective, that's the difference between the two. Both chemistry types have, those excellent technical properties to go along with them. But primarily they serve different color spaces. They both are fit for use for the very demanding application areas, to be able to do that. With the Pyrrolines tending to have a bit higher, from a temperature perspective, they tend to get to those high performance polymer types in plastic areas. This is a general one that you might find useful going forward, that brings them all together in one space to be able to get a, again, another feel for the different areas, and how they match up with respect to the DPP chemistry. So some key takeaways with respect to DPPs. I kind of went through this fairly quickly, but they are the highest performing organic reds. They have their space and their fit and their need in different types of formulations. In there, the design, as we reviewed, drives that durability and the color strength, and then the color shade that each one's put together based on that aromatic unit that's attached in those two locations of the backbone. There's always going to be multiple grades in each area. This is no different than any other chemistry group in there. So, and each one of those is going to be, as it's developed, it's going to be optimized for a specific area in coatings and plastics or inks in there. But it's not to say that it isn't. They're not going to work cross application area. And then, as always, it's important to select the right product for your application area, so that you, as a user of the pigment, can maximize its performance as well as its value. Now, just to give you a flavor of how to use it from a color design perspective, I pulled a few color spaces that I've created over the years from the Color of the Month series to give you a flavor of how you can use DPPs in these types of color spaces and get there. So, most recently, this year, I created this Vermilion Haze, which is more of a that maroon-ish type of color space, utilizing the Pigment Red 264. So taking advantage of the high transparency, that a little bit of that bluish color, in conjunction with other high performance pigments to be able to give that good DOI for the effects pigments that are in there in this formulation, as well as to reach that more of a maroon type of color space. More to the browner side is a combination of just 264 and a gold mica effect pigment, to be able to get that space covered with a very simple formulation with a little bit of carbon black as well, to be able to drive that color more to the brownish side of the red space. And then same thing on the plastic side, same idea. More towards the violet side, again, is a 264 in conjunction with a magenta, red 122, and a blue, CPC blue. Gets that more deeper violet space for that area. And then same with the plastic application area as well. So also in combination with effect pigments to be able to get those colors. And then on the blue side, this is a way to drive a blue more to the red side in here. So, and that's what we've done with the red 264 in conjunction with a blue 15-2 to push it to the red side. So at this point, I'd like to open it up to any questions that you might have.